Welcome to the eighth episode of our series, The Mother Earth. In episode 7, we learned that the two elements Fe and Ni sank down the melts generated in the planetary nebulae of terrestrial planets, similar to what was discovered in the asteroid Vesta. The high bulk density of terrestrial planets, contrasting with those of gaseous giants, is a direct proof which indicates the extraordinary presence of these two elements in the planetary nebulae of solid planets. Comparing the bulk densities with the densities of the crustal rocks, 2.6 to 3.0 grams per cc, of these solid planets, it was envisaged way back in the 18th century itself that the matter inside the cores or in the innermost regions of these terrestrial planets must be very dense. For Earth, the density of the core material was estimated to be in the range of 10 to 12 grams per cc. The high density of core material, as well as the depth of 2,900 kilometers at which it exists in the Earth, could be confirmed much later in the 20th century by detailed seismological deductions. When the solar system came into existence, almost 99% of its total mass was accreted in the Sun itself. Since then only, the Sun acquired a powerful gravity field and also a widely influential magnetosphere. The rest of the mass formed the nebulae of the planets, which inherited their compositions from the nebular clouds blown out during the supernova explosion. While the Sun's powerful gravity field held the spinning planetary nebulae in their orbits around it, its strong magnetic field pulled, attracted, and held closely most of the FeNi and other ferromagnetic elements. That explains the predominance of these elements, limited to the compositions of the terrestrial planetary nebulae. Only the remnant FeNi and other ferromagnesian elements dispersed farther into the asteroid belt, beyond which only the gaseous planets exist, which hardly contain any FeNi in them. But how did the solid planets and the asteroids achieve their highly dense planetary cores dominated by these elements? We have learned that it couldn't have been possible without the initiation and long duration of copious melting and gravity separation of matter within these planetary bodies. Quite certainly, the planets achieved their core sizes also under the influence of the fast, widely growing, strong magnetic and gravity fields of the Sun. The Sun's gravity is about 28 times stronger than that of the Earth. The slow speeds of spinning of Mercury and Venus were also manifested by the torque exerted by the gravitational pull of the Sun. This torque had many different repercussions on the manner in which the planetary nebulae evolved later to solid planets. Mercury being closest to the Sun, its core occupied 75% of its total radius. But the planet could achieve only a feeble magnetic field because of its slow spin on its axis. The cores of Venus and Earth attained a similar size, and the heavy density matter in them occupied about 50% of their radii. But since Venus spins extremely slowly, it has a weaker magnetic field compared to that of the Earth. Within Mars, the core matter could occupy about 40% of its radius. But despite the planet's similar spinning speed as that of the Earth, it has a far weak, almost 40 times weaker magnetic field than the Earth. Thus, the distance from the Sun at which the planetary nebula of the Earth got settled was very crucial for its speed of spinning. The magnetic fields also developed because of the profuse melting initiated within their nebulae. The respective strengths of the magnetic fields reflect the force of gyratory and convective currents within the liquid or fluid phases of FeNi-rich matter present in their cores. The weak magnetic fields of Mars, Venus, and Mercury indicate the near absence of such magnetically susceptible, electrically conductive fluid matter within their cores. The Earth has the strongest magnetic field since a large portion of its dense core is constituted of such electrically conductive fluid matter. During melting and density separation, the outer portion of Earth's core attained a fluid physical state. The matter constituting the outer core could only remain as fluid at the temperature prevailing at that depth of 2,900 kilometers from surface. This indicates also that the magnetic field of the Earth is antique, at least 4 billion years old, and its strength has been maintained ever since. The force of convection in the fluid matter largely depends, of course, on the different spinning speeds of the planets. The phase difference between the liquid outer core and solid inner core of the Earth got verified and substantiated later by seismological deduction. It was revealed that unlike the primary earthquake waves, which penetrated and traveled through fluid matter, the secondary earthquake waves were blocked. They could not travel through fluid media. This discontinuity between the mantle and the core of the Earth, caused by the contrasting difference in the density and physical state of matter, has been referred to as the Gutenberg discontinuity. The melting and gravity separation, though achieved in the initial few years, it is still remaining to reason out how there has been a continuous supply of heat energy from the inner core to the outer core, because of which the matter constituting the outer core has remained in a fluid state for the last 4 billion years. It is the heat gradient, isn't it? From high in the inner core to low in the outer core, which has maintained the Earth's magnetic field. Similarly, the Sun's magnetic field has been maintained by the continuous movements of electrically charged ions inside it, and the heat transfer during the exothermic nucleosynthesis reactions, together, of course, with the sun's rotation. The sun has a magnetic field twice as strong as that of the earth. It penetrates the interplanetary space well beyond the last located planetary body of the solar system. The Jovian planets also have a fairly strong magnetic field, but the cause is different. These planets, being far less massive, no nucleosynthesis reactions could be initiated in them. But the hydrogen and helium constituting them undergo physical transformation to a metallic liquid phase under excessively high pressure, say more than 100 million atmospheres. The liquefied metallic hydrogen and helium being superconductors of electricity, the gaseous planets also maintain strong magnetic fields. The separation of cores in the planetary nebulae resulted also in mass concentration within them. That should have lowered the moment of inertia and increased the angular velocity of the already spinning planetary nebulae. Planets acquired their gravitational force during the time their cores stabilized. The strong gravitational pull of Jupiter was witnessed when the comet Schumacher-Levy 9 broke into many parts while colliding with Jupiter from July 16th to 22nd, 1994. That spectacular event compelled planetary scientists to speculate that such collisions could have taken place in the initial nebular histories of terrestrial planets as well. During the melting and core formation, the planets achieved their surface gravity also, the effective mass being the mass of the core. Gravity is also referred to as the acceleration due to gravity, denoted by the letter small g. The present value of small g for Earth is 9.8 meters per second square. The gravity of other planets is expressed in terms of the multiples of small g. As for example, Jupiter has the surface gravity of about 2.5 g. The Earth retained its hydrosphere and the atmosphere on its solid surface only because of its gravity, its distance from the Sun, and its speed of rotation. Mercury, Venus, and Mars could not. In this episode, we have learned why the terrestrial planets have high densities, large cores, different surface gravities, and different strengths of magnetic fields attained during the process of core formation. We have learnt why the ferromagnesian elements are limited mostly to the terrestrial planets. We have also learnt why only the Earth amongst solid planets has the strongest magnetic field along with the highest bulk density and gravity. Why the Sun has the strong magnetic field that penetrates through the interplanetary space well beyond the last planetary body in the solar system. We will learn more about the heat inside the Earth, the significance of its internal structure and composition in the next episode. Thank you.